Good evening, everyone. Am I audible? Hope you are able to see my screen. We'll just wait for 2-3 minutes and start the today's live session. Okay, let's get started. Welcome to the second live session of Digital Design with Verilog. First, let me introduce myself for the students, those who are joining for the first time. My name is Bijun Elsa Bibi. I am a research scholar from IIT Palakkad. and I will just quickly go through the logistics of this live session. So every week, I will conduct the live session on Sunday. It is from 6 to 8 p.m. In this live session, we will have a quick recap of the previous week content, and we will solve problems which are similar to your assignments. It will not be the same questions, but it will be the same pattern questions. And time will be given for you to solve each problem, and you can post your responses in the chat box. If you have any doubts from the previous week content, you can also post the questions after the problem solving session. Or if you want me to particularly solve any of the problems, that also you can post it in the chat box at the end of the problem solving session. And after the session, you will have the recordings and the slides. It will be shared through a sheet, which will be, you can find it from the course web page. Yeah, I have uploaded the week 1 live session recording in the sheet. You can get it, the link from there. After this class, I will upload the recording of this live session. And the syllabus of this course is in the first half, you will be learning about switching algebra, the various number system, the Boolean algebra, and how you can minimize the logic, and mostly about the combinational logic blocks like mux, demux, encoder, decoder. And you will have the introduction to the HTML language called Verilog. And in the second half, you will be learning about the sequential circuit designs. For example, flip-flop, registers, counters, FSM. And at the end of the course, you will learn about the basics of the FPGA architecture. So last week, we learned about switching algebra, the properties of switching algebra, and we have seen how we can represent the switching algebra in SOP format and POS format, the canonical forms. Then we also looked into different number systems. This week is a continuation of previous week. In this week, you learned about binary arithmetic, binary addition, subtraction, how we can represent the signed binary numbers, how to represent the signed binary numbers using one's complement and two's complement. Then after that, you have learned about the binary binary weights and non-weighted binary. So in weighted code, you will have BCD. In non-weighted code, you have XS3 gray code. That is also called cyclic code. And at the last lecture, you learned about the error detecting and correction codes. So these are the different topics you will have in the week 2. I hope you have all watched the week 2 videos. So I'm straightly going to the problem solving session. We will discuss each topic during the problems itself. So first question is, you have to find the decimal equivalent of so binary number is given. So you have to find out the decimal equivalent of one's complement of this binary number. Okay, regarding the assignment scores, they will publish the results after the deadline. Okay, so this is the binary number. So one's complement, that is, you are taking the complement of each bit. So here, 0 complement, that will be 1. 1 will become 0, 0, 0. The decimal equivalent will be 1. 1 is the correct answer. Next question is, given a binary number, this is the binary number 1010. What will be the difference of its decimal equivalent, 2's and 1's complement? the question, you need to find out the difference of its decimal equivalent, 2's and 1's complement. So first of all, you have to find what is the 2's complement of this binary representation, then 1's complement of this thing. Then you need to find the difference of its decimal equivalent. How you are getting 4? How you got 4? First, to find out 2's complement of this number 1010, then 1's complement, then take the decimal equivalent of both and do the subtraction. Yeah, 1 is the correct answer. So how we can solve this problem? First, we are going to take the 2's complement. Okay, first we will take the 1's complement, just flipping the bits. That will be 1 0 1 0. This is 1's complement. For finding out 2's complement, you have to add with 1. Zero, carry 1. Then 1 0. This is 2's complement. So instead of adding 1, you can do an easy way to find out 2's complement. That is, you alternate way. You have the binary representation. So till the first one, you need to start from the LSB, okay? So 0 you can write. Till the first one, you have to write it as same as a input number, okay? 0, 1. After this 1, you have to take the complement. So this will be 1. This will be 0. So this is the 2's complement. Another example, if I show you 1101, you have to write same like input till the first one. So here LSB itself is 1. So after this, you need to take the complement 1, 0, 0. Got it? So 1's complement, this is 5, the decimal equivalent of this value. This is 6. So we have to take the difference of its decimal equivalent 2's and 1's complement. So 6 minus 5, that will be 1. All of you got the answer? Now we are moving to the next question. Excess 3 chord of 5. Are you talking about this question? So this is like they asked about the decimal equivalent. So it will be 1. So the options they were given, it was in decimal equivalent. So when I share the slides, you can also go through the options as well. Excess 3 chord of 5. So how you got 1011? So here 5. What is the binary representation of 5? That is 0, 1, 0, 1. Excess 3 code we need to add with 3. 0, 0, 1, 1. So 1 plus 1, 0, you will have carry 1. 1 plus 1, 0, again you will have carry 1. 1 plus 1, 0, you will have carry, then here it will be 1. So the answer is 1, 0, 0, 0. Excess 3 representation. Now I will also give you some similar question of excess to equivalent. Find the excess 3 equivalent of 237.75. All of you solve this question, tell me the answer. Remember one thing, excess 3 is also a type of BCD code. BCD is a weighted code. So for BCD, the weights will be 8421. Here the integer part is 237. So the x3 equivalent of 7, that will be 10, 3, 6, 2, it will be 5. Now are you able to write the binary x3 representation? All of you, what you have done is you have converted the decimal to binary, but we need the x3 code. So x3 code is also a type of BCD. The decimal part is 75. Here also x3 will be 10 and 8. All of you understood this thing? This is the x3 equivalent of 237.75. All of you understood this thing? Now, the next question is find the decimal equivalent of x3 number. There is 110010 1 0 0 0 1 1 0 1 1 1 0 1 0 1. You need to find the decimal equivalent of x3 number. The number is 1 1 0 0 1 0 1 triple 0 1 1 point 0 triple 1 0 1 0 1. In the previous question, decimal number was given. You had to find the x3 number. In this question, x3 number is given. You need to find the decimal equivalent. Yeah, all of you got it correctly, 970. So here it is 3, 10, 7, 5. We are dividing, we are subtracting minus 3. So it will be 2, 0, 7. So the answer is 970 point. Next question is given two decimal numbers x equal to 31 and y equal to 25. Consider their 2's complement in 6-bit representation for addition or subtraction. What is the value of y minus x? Okay, the question is why do we use existing code if such a large amount of bits required processing information? So actually, this is also a type of binary coded decimal. That is, if you look into hexadecimal or octal, that is also for grouping the binary number. But this one is easy to handle using BCD. But BCD has a disadvantage if you take two numbers, sum of two numbers when you go for the arithmetic. It cannot handle more than 9. That's why you are using X3. So how you can solve this problem? Y minus X. So here you can solve like Y plus minus X. And for representing the negative numbers, you can use the 2's complement of X value. Then you can add with Y. 0.00110 is the wrong answer. You have to take the 2's complement of 31. Y is 25, then 100,110, that is also wrong. So it is a standard way to represent the negative number in 2's complement. So you have to take the 2's complement of 31. First, tell me the binary representation of 25. Zero, one, one, zero, zero. This is minus 31. So you have to take the 2's complement of 31. So what is the 2's complement of 31? Zero, one, 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 zero. Is that the 2's complement? 2's complement is 100,111. How we are getting 2's complement of 31? So first write the binary representation of 31. 0001, that is binary representation of 1, right? This is the binary representation of 30. Now 2's complement is 0001, that is not the 2's complement. This is the binary representation. Now take the 2's complement. Yeah, 100001, that is the right answer. So you need to start from LSB. So this is the first one. Then after that you have to flip it. So this is the MSB is 1, that is negative, minus 31. This is the sign to be. Now add this. So usually we use 2's complement to represent the negative number. So this is a binary representation of minus 31 in 2's complement form. Yamuna is right. Okay. Now 0 carry 1. 0 1 1 1. This is the answer. All of you understood this? We are taking 2's complement to represent this negative number. So you have to perform the following binary addition. The numbers 275.75 plus 37.875. So this is the number is given in decimal, plus you need to convert it into binary. Then you have to do the addition. Yeah, I will show the question 6 again. Here y minus 6 we have to do. This thing we can write it in this way, y plus minus x. So here minus x is minus 31. We can use 2's complement to represent the negative number. So we are taking the 2's complement of minus 31. So the minus 31, we can represent it in this way, 10001. Then we will be doing the addition with 25. So final answer will be 111010. Can I move to the next question? Okay, this question you have to do the binary addition. First, you have to convert this decimal to binary, then you have to do the addition. First, tell me the binary equivalent of this decimal value. Yeah, 100,111,00.101. This is the correct answer. So find out the decimal equivalent of this value. The other answers are wrong. This is the final answer of the binary addition 100,111,001.101. Find the decimal equivalent of this binary value. Wait, 8.158. That is wrong. Yeah, this is the you are talking about the binary representation of 275.75, right? Paisa 100,001. Yeah, that is correct. And 00010011 point. This is the binary representation of this value. All of you know how to find this binary representation. Do I need to show you? Or all of you got it? This binary value of this decimal number? Okay, then give the value of 37.875. Yeah, all of you got this answer. This is the binary representation. The decimal equivalent will be 313.625. Here, the decimal values are given 275.75, 37.875. First, you have to find out the binary equivalent of decimal values. Okay. After that, this will be the binary equivalent of this value. So this has only 6 bits. The rest of the bits you can fill with 00. Then do the addition. 0 plus 1, that will be 1. 1 plus 1, 0. Here there will be a carry. Then 1 plus 1, 0. Plus 1. The carry you need to add. So 1 will come here. Then there will be a carry here. 1 plus 1, 0. Plus 1. 1 will be here. Then again carry will come here. 1 plus 1, 0. 1 carry will be here. You have to do the addition. So you will get this value. Then once you get the binary value, you need to find out the decimal equivalent of this binary number. Surendra, you got it? This is just binary addition. Okay, then we are moving to the next question. The question is, what is the representation of the number 7 using code words if the weights are given as follows? 2421 is the weight. And this is the correct answer. So here 2421, that is 7. Here it is 4. Here it is 1. Here it is 9. So this is the right answer. Next is a very simple question. Which question you want me to explain, Yamuna? Eighth one. So here the weights are 2, 4, 2, 1. And what is the representation of number 7? We are putting 1 here, then it will be 2. 2 plus, we are putting 1 here, 2 plus 4, 6. Now 1 is also needed. You can put here 1, 0. 2 plus 4 plus 1, that will be equal to 7. Here, if you put 1, 0, 1, 0, 2 plus 2, that will be 4. 0, 0, 0, 1, this will be 1. 1, 1, 1, 1, 2 plus 4 plus 2 plus 1, that will be 9. So this will be the representation of 7, 1, 1, 0, 1. Okay. So moving to the next question, what number you should add with the BCD code in order to achieve XS3 code? These are the options. The option that is XS3 you have to add with gray code is given. You need to find the binary number. So once you find the binary number, you have to convert it into decimal. Options are first class recording is available. You can get the link from the Google Sheet which is shared by the NPTEL team. You can find it in the course page. Yeah, last week we solved problems from number system, switching algebra and all. And finding out the binary code, 0 will be G0, B1 will be B0 XOR G1, B2 B1 XOR. So it will go like that. So here it will be 1, then 1 XOR 0. That will be 1 XOR 0 will be 1. Again 1 XOR 0 will be 1. 1 XOR 1, that will be 0. 0 XOR 0, 0. 0 XOR 1, 1. 1 XOR 1, 0. This will be the binary number, and 114 will be the decimal equivalent of this binary. All of you understood? Find the binary equivalent of this gray code. First bit, you have to write it as it is. Then 1 XOR 1, that will be 0. 0 XOR 1, that will be 1. 1 XOR 1, that will be 0. So this is the binary equal. Now binary code is given. You need to find out the gray equivalent. Here, the G0 bit will be G0. So it will be 1. Then G1 will be this XOR this one. That will be 0. Then 1 XOR 0, that will be 1. 0 XOR 1, that will be 1. So this will be the gray code 1 0 1 1. do the binary subtraction of these two numbers. First, you have to find out the binary equivalent of these decimal numbers, then do the binary subtraction. Tell me the binary representation of 27.75. Binary representation of 27.75. Post your answers in the chat box. One, 0, 1, 1, 1. And 14.375. $14.37. All of you got this answer? Here 0 minus 1, 1, borrow bit. Here it will be 0, 0 minus 1, 1, borrow bit, 0, 0 minus 0, 0. Then here it is 1, 1 minus 1, 0, 0 minus borrow, 0 minus 1 will be 1, and borrow. Here 0 minus 1 will be 1, last will be 0. All of you got it? All of you got the answer? Okay, shall we move to the next question? This is a true or false question. For even parity error detection, the parity bit is set to 1 if the binary representation of the number has an odd number of ones. Is it true or false? Shweta is telling true. What about others? In even parity error detection, if the binary representation of the number has an odd number of ones, the parity will be 1. The statement is true. If it has even number of ones, the parity will be 0. So this statement is true. Next question is the minimum distance between two valid codes must be x for error correcting code to capture single errors. And what will be the x? That is the minimum distance between two valid codes in the error correcting code. We have two valid codes. We are talking about the single error, single bit error. So you will have some information which is in binary. One in that information is corrupted. So one of the bit is flipped. So the minimum distance here from valid code to the error code, it will be 1. And from this valid code to another error code, that will be also 1. So this both the error codes cannot be the same. So there will be a distance of 1 between both the error codes. So total will be 3. For example, this is one of my valid code. So this is one valid code. This is another valid code. So from this valid code, the distance here is 1. This bit is changing. From this error code, here the error code, it will be 000. So if you change this thing, this 2 bits, then total 1 plus 2, 3. Here taking some example, this is the valid code, this is the information we want to send. Okay. So here the sender is sending this information, but the receiver side, we are getting the corrupted code. So this is the corrupted information. Instead of 1, it is getting 0. Here, instead of 8, it is getting 9. So the distance between the two valid codes, that will be the minimum distance, that will be 3. Next question is, which of the following relations is true for harming codes error correction? Where M is the message length, K bit parity. Here M is the message length, K is the parity. For a Hamming code, you will have M plus K plus 1. 1 will be the for the no error state. This is the parity bit and this is the number of message bits. So this should be less than 2 raised to K. So this is the number of parity bit. So parity bit, the number of possible combinations with the parity bit is 2 raised to K. It should be greater than or equal to M plus K plus 1. We will solve one example of Hamming code. Write the Hamming code for 000 using even parity. Parity means if you have even number, if it is even parity, if you have even number of ones, then the parity bit is 0. And if you have odd number of ones, then the parity bit is 1. Here the message bits are given. You need to find the value of K1, K2 and K3. So how to find it? K1, K2, K3. Here 2 raised to K greater than or equal to M plus K plus 1. So you need to write all the combinations of K. Okay, here it is for 7 for harming God. The order of representation is K1, K2, M1, K3, M2, M3, M4. K1, K2, K3. If there is no error, it will be 0, 0. The parity will be 0. Sorry, here we are assigning the bit position. It doesn't have any error. It will be 0. If it is 0, 0, 1, you have error at bit 1, the position. 0, 1, 0, 2, 0, 1, 1, 3, 1, 0, 0, 4, 1, 0, 1, 5, 1, 1, 0, 6, 1, 1, 1, 7. Now look at this. This K1 is influencing the bits 4, 5, 6, 7. K2 2, 3, 6, 7. K3 1, 3, then 5, 7. So from this, you have first one is 4, 5, 6, 7. 4, 5, 6, 7. You have the values for 5, 6 and 7. 4 is not there. 0, 0. In the question, it is given as even parity. So what value we should give here? We should give 0. If you give 1, then it will have odd number of ones. So K1 value is 0 now. Now K2 2, 3, 6, 7. So here 2 is not there. 3 and 6, 7. 0, 0, 0. So even parity, this value will be 0. So K2 will be 0. Now 1, 3, 5, 7, K3. 1, 3, 5, 7. That will be also 0. So answer will be 0, 0, 0, 0, 0, 0, 0. This is a Hamming chord representation. So with this, we are coming to the end of this session. Do you have any other particular question from this week content? Then we can solve it in the next class. So these are the references. You can go through it. Okay, thank you.